Hello everyone, my name is Mamer Zapaidari, a PhD student at Simon Fraser University. In this video, I work on the iris flower classification for my second machine learning course assignment. The goal was to classify three species, Setosa, versicolor, and virginica. As you can see here, the size of the petals and sepals is different for these three species. As a result, we should use four input features: sepal length, sepal width, petal length, and petal list for this classification. This dataset contains 150 samples with 50 from each class, so it is a balanced classification problem. Before training the model, I first perform a data analysis to understand the dataset. The iris dataset has four input features, as I mentioned. From the per plot here, I observed that Setosa is clearly separated from the other two species, especially when petal length and width are used. This means Setosa is an easier class to classify. However, versicolor and virginica are more closely related and show some overlap, so I expected most classification errors to occur between these two classes. The correlation heat map also supports this conclusion. Petal length and petal width have a very strong correlation of about 0.96, meaning they increase together and carry very similar classification information. This tells me that petal measurements are the most important feature in this dataset. Overall, this data analysis shows that the main classification challenge is not identifying Setosa, but separating versicolor from virginica. I use a strategy for random sampling to split the dataset into 90% training and a 10% testing. A stratification is important here because the test set is small, only 15 samples, so I wanted to preserve the class balance. The test set contains 5 samples from each species. Let's go to the machine learning model. The first model was a decision tree. I tested different maximum depth from 1 to 10. At depth 1, the model underfitted with an accuracy of around 0.67. This means one split was not enough to classify all three classes. The best decision tree was depth 2, with validation accuracy around 0.956 and test accuracy around 0.933. When the depth increased, training accuracy reached 1, but the validation accuracy did not improve. This indicates overfitting. The decision tree visualization is also useful. It mainly uses petal width to separate the classes. This agrees with the data analysis where petal width and petal length were the most informative features, so the model result is physically and visually understandable. The second model was KNN. I tested different values of K from 1 to 10. With K equals to 1, the model achieved perfect training accuracy, but this can indicate overfitting because it relies too heavily on individual training samples. The best validation result occurred at K equals to 9 with a validation accuracy of around 0.97. On the test set, KNN correctly classified all 15 samples. The third model was random forest with 100 trees. I explored different maximum depths. Interestingly, the best validation accuracy occurred at depth 1. This shows that the dataset is simple enough that even shallow trees can separate the class as well. The random forest test accuracy was 0.933 with one versicolor sample misclassified as virginica. After checking accuracy, I examined the confusion matrices to identify where the model made mistakes. All three models classified Setosa perfectly. Errors occurred only between versicolor and virginica. The decision tree misclassified one virginica as versicolor, and the random forest misclassified one versicolor as virginica. This highlights that the main challenge is the boundary between versicolor and virginica. KNN achieved 100 accuracy on the small test set, but caution is needed in interpreting these. Overall, the confusion matrices indicate that petal features distinguish Setusa well, but overlap between versicolor and virginica, which leads to occasional errors. Comparing the three classifiers, KNN gave the best test result, decision tree was the most interpretable, and random forest was robust, but did not improve the result for this small dataset. The confusion matrices showed that Setusa was always classified correctly. The only mistake were between versicolor and virginica, which matches the overlap observed in the previous plot. My main criticism of the result is that the test set contains only 15 samples. Therefore, a single incorrect prediction reduces accuracy by about 7%. This means I should not overinterpret the 100% test accuracy of KNN or the overfitted decision tree. A stronger evaluation would use repeated stratified cross-validation and report a mean and a standard deviation of accuracy. Overall, the results show that petal measurement are the key features. KNN performed best for this split, and model complexity should be controlled to avoid overfitting. The most important learning from this assignment is that high accuracy alone is not enough, and I need to compare training, validation, and test performance, examine the confusion matrix, and connect the model's behavior back to the data distribution showed in the data analysis.